Hello everyone. I'd like to present our ICCV25 highlight work, with the title as Feature Purification Matters, Suppressing Outlier Propagation for Training-Free Open Vocabulary Semantic Segmentation. I will discuss the introduction, methods, research results and conclusion, respectively. At the first, I'd like to talk about what is the open vocabulary semantic segmentation. In the field of visual understanding, deep neural networks have made impressive advancements in various tasks like segmentation. However, most approaches operate on the closed-set assumption, which means that the model can only identify predefined categories that have been present in the training set. Recently, open vocabulary settings were proposed due to the rapid progress of vision-language pre-training. These new approaches seek to locate and recognize categories beyond the annotated label space. It is more general, practical, and effective than zero-shot settings. Specifically, as shown in A, the closed set means the models are trained and test within the closed set knowledge C sub B. And in B, the zero-shot setting is that a model is trained in C sub B and have to classify unknown classes C sub N into specific categories. In C, the open vocabulary setting means the model can classify novel classes C sub N with the help of large language vocabulary knowledge C sub L. It's the difference between settings. Then, what is the limitation? To leverage the rich large language vocabulary knowledges, we have to employ the vision language model like CLIP as the backbone to extract dense features for both images and texts. However, CLIP still suffers from several limitations. First, as illustrated in the left figure, the self-attention mechanism of CLIP is insufficiently effective. For instance, the token marked with a red star fails to attract attention from other relevant tokens. It results in a weak semantic representation in CLIP's dense features. In addition, most open vocabulary models rely on fine-tuning with downstream datasets, which inevitably impairs CLIP's inherent zero-shot capability. These issues both restrict the effectiveness of CLIP for open vocabulary segmentation. Next, I'd like to share our work. To generate clean dense features, we begin by analyzing the CLIP's self-attention mechanism. As shown in the left figure, regardless of which patch token is selected, marked as red star, it always exhibits abnormally high responses to a few specific patch tokens, which we termed as outliers. This behavior not only suppresses its self-attention but also other semantically related tokens' attention. It ultimately results in a noisy dense feature representation. Motivated by this observation, our work aims to design a simple yet effective approach that can adaptively detect and eliminate these outlier activations to purify the dense features for more precise segmentation, as shown in the right figure. Then, it is the overview pipeline of our solution. It contains 4 main modules: a frozen CLIP backbone for feature extraction, a self-adaptive outlier mitigator, SOM, at each image encoder layer for outlier detection and elimination, a semantic-aware attention enhancer, SAE, at the last layer to emphasize attention values of relevant semantic regions, and a hierarchical attention integrator, HAI, for object-centric feature representation. First, the image and text descriptions are input to the CLIP encoder for the image feature and the text feature. Among the CLIP image encoder, our SOM is added after each transformer layer to mitigate the outliers and generate the purified feature for propagation. The final feature is input to our SAE, which replaces the final transformer layer. SAE emphasizes the attention values of relevant semantic regions to generate the strengthened semantic feature F sub SAE. After that, our HAI extracts the multi-layer attention maps from the image encoder to further refine F sub SAE for the final semantic feature F sub vis. Finally, the segmentation result is obtained by calculating the cosine similarity of the final semantic feature F sub vis and text feature F sub txt. The key and object of this work is how to generate clean dense feature F sub visual SOM, which is our key innovation. By simply comparing the difference between self-attention weights, the matrix diagonal elements, and the CLS token attention weights, the first row elements, we can detect the outlier token. We locate them in the dense feature, and use average filter to mitigate the outlier and maintain the semantic consistency. Then, SAE, which has been confirmed as an effective way to enhance the feature affinity by using the modified self-attention for local representation. And HAI, which uses self-attention matrix from shallow layer for object-centric representation. As shown in the above figure, our method can effectively address the noisy feature representation and generate the clean features. We also conduct comprehensive ablation studies to demonstrate the effectiveness of our proposed modules. We evaluate the effect of different modules in C, and layer feature aggregation in D. We also evaluate the robustness of our method on different backbones in E. The quantitative segmentation results are shown in the table. Our method outperforms existing SOTA methods, regardless of whether an additional backbone is introduced or not, in a training-free manner. Our SFP can predict more accurate and complete segmentation maps, yet other methods exhibit significant noises, unveiling its limitations in spatial localization. These results indicate that our SFP has a good ability to predict comprehensive segmentation masks. Our work, SFP, confirmed that feature purification does matter for OVSS since it can generate cleaner visual dense features for image-text alignment. It's also simple yet effective. Our future plan is to explore how generate cleaner image-text cosine similarity maps from the perspective of both image and text features, not only limited in the visual domain.